This unit, we're going to be looking at exponential functions and the inverse of exponential functions later on. But today we're going to focus on these exponential ones so that you can know how to graph them, that you can write an exponential equation in this form. This is the form of exponential functions, and that you can also solve exponential equations. Okay, so this first problem says Sam is working in a biology class with a petri dish of bacteria. He estimates that a colony of about 25 bacteria in there. Assuming the entire population of bacteria doubles every hour, how much bacteria will Sam find after 5 hours? Well, we could simply keep doubling here and find this out, maybe make a little table here, and figure out in 5 hours how much are we going to have. So we know to start with there was 25. If it doubles after 1 hour, we're going to have 50. If it doubles again, we're going to have 100. If it doubles again, we're going to have 200. If it doubles again, we're going to have 400. And if it doubles again, we're going to end up with, looks like 800 bacteria after 5 hours. So the answer is 5. But we don't want to have to do this because if it said how much are we going to have in 450 hours, we wouldn't want to keep doubling and making a table like this. We'd be sitting here forever. So we want a faster way of getting to that answer. And how we're going to do that is to work with exponential functions. We've looked at a bunch of functions already. We've looked at linear functions, that's straight line graphs. We've looked at quadratic functions back in unit 4 and looked at how you can graph those, or parabola. We've looked at other polynomial functions in unit 7. We looked at square root functions in unit 8, and we also looked at rational ones in unit 9. So we got a bunch of functions we've looked at. This last type that we're going to look at in Algebra 2 here is what's called exponential functions. That is any function where your variable is going to be in the exponent. Okay, we haven't had that happen yet. And any exponential is going to be in this form of y equals a to the b, or a times b to the x power. Some properties of this function. This is going to be a continuous function and one-to-one, meaning that there is an inverse function to it. The domain of any exponential is the set of all real numbers. We could put any number in for that exponent x and get an answer for y. The x-axis is an asymptote. Okay, that means as you get closer, as you get bigger, smaller, it's going to eventually go towards the x-axis. The range is all the positive numbers. You can't get a negative number when the first value here, a, is bigger than 0. Now, if it is less than 0, if a is a negative number, then you will have all your y's will end up being negative. Okay, the graph's going to contain this point. A then is your, whatever a is going to be your y-intercept. Okay, so in this equation, whatever a is, that's your y-intercept. That's where your graph is going to start. The graphs of these are reflections across the y-axis. So if you get something where b is 1 over the reciprocal, then it's a reflection across the y-axis. All right, so some things about this equation. When we're doing these, a, since it's your y-intercept, that is your starting value. It's where your graph crosses the y-axis. Y is going to be your ending value. This exponent we talked about, x, that's how many times you are repeating the multiplication. And then b, that is your multiplier. That is what is happening in your problem. So if we go back to the one we just looked at with the bacteria, we should be able to get the same answer using this y equals ab to the x equation. Okay, our a is our starting value. What was the starting value of this one? 25. So 25 would be a. Okay, b, that's our multiplier. In this case, our multiplier would be that it's doubling. So if it's doubling, that means it's being multiplied by 2. X is the number of times. The number of times we're doing this is 5. We're doubling 5 times, so that's our exponent. We want to find the ending value. So if we put this in our calculator, we should get the same answer of 800. So going on to calculator, if we type that little equation in, 25 times 2 to the power of 5, we get the same result, 800. So that would be a quicker way of coming up with an equation to figure out these types of problems. And that's what we got. That's what we're going to try to get you guys to do here. All right, one last thing with some properties here. Down at the bottom, that you guys can see some graphs of exponentials. It kind of highlights some of the things we talked about here. This is an example of exponential growth. And we'll talk about exponential growth as we go through here. On this side, it's very small, and then it grows very large as you come up here. Notice that it crosses through at 1. And the reason it crosses through at 1 is in this equation, it's y equals 1 times 2 to the x. Our starting value is 1, so that's the place it crosses through the x-axis. Okay. Also, we said that it's the x-axis is an asymptote. If we go to the left here, our graph gets closer and closer and closer here to 0, meaning it never touches that line. It just keeps getting closer and closer and closer. This other graph over here starts big and then gets closer to 0 as you go to the right. This is what's called exponential decay, and we'll get into that throughout the unit. That means we're going to get smaller as we go to the right. This is going to get closer and closer again to 0. Again, where it crosses through here is at 1. That's our y-intercept because this is 1 times 1/2 x. All right, so we're going to do some graphing here. When you're graphing these, you can make a little table, come up with points, and see what you get. So if we were to plug these different numbers in for x, we should be able to get the y value. So let's say we plug in 2 here. What is 3 times 2 squared? Well, remember, you got to think back way back to the first unit we did. If we're doing order operations here, we got to make sure we do our exponent before we multiply. Do not multiply 3 and 2 here. So 2 squared is 4. 3 times 4 is going to be 12. So that's the value there. If we do the same thing with 1 there, 2 to the first power is 2. 3 times 2 is 6. And we could keep going like this. If we put 0 in, we know anything to the 0 power is 1. And 3 times 1 would be 3. And so on. You can probably see the pattern going over on there at the right. Looks like each value, as we keep going here, is times 2 from the one before it. This is times 2. This is times 2. So we could do that, or we could go the opposite way and divide by 2 to get the other ones. Or probably the quickest way, rather than doing any of that, is to use your calculator. You should be able to put this function into your y equals screen here, and then pull up the table that way. So if we enter this function, 3 parentheses 2 to the power of x, we can then select our table, and it gives us all these values that we are looking for in here. So if we scroll here, all those same values are being shown at -1. We can see it's 1.5. If we keep going on our table here, at -2, it's 0.75. And at -3, it's 0.375. Okay, so if we graph those out now, we'll see what this one looks like. So at -3, it's 0.3. That's probably right about there. At -2, it's 0.75, which is about 3/4. At -1, it's 1.5. At 1, it's 6. Or sorry, at 0, it's 3. At 1, it's 6. And at 2, it's 12, which is going to be up here somewhere. So if we connect these, there's the graph of this one. Okay, notice some things we talked about from before. What's our y-intercept? 3, because what was this number? 3, that's your y-intercept. Okay, and then this problem's just going to keep doubling every time, so it's going to start going up very fast here on this right side because the values keep doubling. This side's getting closer and closer to 0. The other thing they want us to do is state the domain and range on this one. Domain would be all real numbers. We could put any number here in for x and get a result. Our range, okay, if we look at our graph, it's never going to come down in this negative part. So our range would be that y is always going to be bigger than 0. It won't ever equal 0. It's always going to be positive number. All right, let's do the same thing on this next one. So on this next one, we can, again, plug in the numbers, or let's use our calculator and come up with the table. So let's change our function here to 2. And then we got 1/2, 1 divided by 2, to the power of x. And we can come up with our table here. Now, one value we should know already, what is it going to be at 0 here? That's our y-intercept. Our y-intercept should be 2 here. Over on our graph, this should cross through at 2 because that's our starting value. Okay, the rest of them we should be able to get from the table now. At -3, it looks like this one's 16. At -2, we get 8. At -1, it's 4, and you should be able to kind of see the pattern. It looks like it keeps, as we go down here, dividing by 2, so this one's going to be 1. And if we divide 1 by 2, we're going to get 0.5. So this one is going down by half, because what's the multiplier? Half. It's being half of what it was before on each value. So at -3, it's 16. That's kind of off our graph here. -2 would be 8. Be there. At -1, it's 4. Be there. We already got 0, 2, 1, 1, and 2/2. So this graph is going down like this. This is what's called exponential decay. It's getting smaller and smaller as we go, as our values get bigger. Okay, domain on this one would also be all real numbers. We can put any number in for x on this one, and we can find the y value. The range, the y values, again, never come down in this negative part. That's always going to be a positive value greater than 0. All right, so we should know the difference between exponential growth, where your graph's increasing as you move to the right, and exponential decay, like this last one, where it's decreasing to the right. So some word problems you're going to get into might ask you some stuff. So you should know the difference of what things do. If you have a car, generally over time, cars are going to decline in value. Now there's some exceptions. If you have some classic car that you might restore, then yeah, maybe the value increases. But for the most part, your average car is going to decline in value as you drive and get wear and tear on it. Jewelry, gold, that kind of stuff generally increases as exponential growth over time. The value is going to keep increasing. Same with homes. Your house, as long as you maintain your house, house values over time are going to increase in value. Technology, computers, probably pretty obvious, they're going to decay over time because new stuff comes out and it becomes less valuable because there's bigger, better things. Okay, some words you should also look for when you're doing these. Any type of growth would be words like increase over time, grow, of course, anything that says that. There's a word called appreciation. That means increase. Some words you should look at for decrease would be decay. Depreciation means decline in value. That's like your cars depreciate. Decrease. All those types of words all mean are going down. So those are some words to look for in word problems as well. All right, so how do you determine whether a function's exponential growth or exponential decay? Your b value, okay, your multiplier. If your b value is greater than 1, then you have exponential growth. If you have a b value that is less than 1, you're going to have exponential decay. Okay, so let's look at these two and see what we have. In the first one, A, what is our b value? 1/5. Is that a number bigger than 1 or less than 1? 1/5 is definitely less than 1. This is going to be an exponential decay equation here. You're going to get a graph where it decreases over time. Okay, let's look at B. Our multiplier here, 1.2. 1.2 is bigger than 1. This is going to be exponential growth. You're going to get a graph on this one that over time it's going to increase in value. All right, looking at some word problems then and some problems where you're going to have to use this stuff. On number 3, it says suppose you buy a car for $15,000 and its value decreases at a rate of 8% per year. Write an exponential function for the value of the car after X years. Okay, so in this problem, we want to find out all these things we talked about before. What's our start value? What's our multiplier? How many times are we doing it? And what's our ending value? All right, well on this one, our starting value, they told us, that's 15,000. Okay, what's our multiplier? We'll come back to that one in a second here. We don't know our ending value, and we also don't know how many times we're doing this right now. So that's going to be a variable. All right, so it says it's decreasing at 8% per year. So we got to figure out, what is that going to be? Well, if we start always at 100%, and we're decreasing by 8%, that means our value each year is going to be 92% of what it was the year before. Now, when you're putting this in an equation, you can't put it in as a percentage. We know percentages always have to go in as a decimal. So if you change 92% to a decimal, that's going to come out as 0.92. 0.92 is our multiplier. Okay, so what's our value of our car after 4 years? So now what we need to do then is just take this and put it in for X. That's the number of times we're going to be doing that. So we got 15,000 times, it's always 92% of what it was the year before, to the 4th power. So now if you put that in your calculator, you should be able to calculate the value of this car. So 15,000. 0.92 is our multiplier. That's less than 1. This is going to be exponential decay because we see the word decrease in there. Power is 4. So it looks like the value of the car decreases to $10,745.90. All right, let's try another one. It says, suppose you start an experiment with 45 bacteria that double every hour. Write an exponential equation. So again, we want to use this form, y equals ab to the x. Let's plug everything in. Starting with 45, that's going in for a. Okay, doubling every hour, that means times 2. That means 2 is going to be our multiplier. Okay, so our equation becomes y equals 45 2 to the x power. Now, if we want to know how much bacteria do we have after 4 hours, that's how many times. Y equals 45, 2 to the 4th power. And if you put that in your calculator, you should come up with 720 bacteria. All right, let's look at another one. Now, this next one's a little bit different. Here, they're going to give us some information on a table over here, and we're going to have to figure out using this table what the equation is. So they tell us that this substance decaying, exponential decay, and at 1 p.m. there was 1,250. At 4 p.m. there was 10. Okay, so we got to use that information to figure out what our equation is here. Okay, so first thing we want to find out, what's our start value? And they tell us on here, it looks like since we're starting at 1 p.m., that's going to be our A value is 1250. Okay. Our B value, our multiplier. Now, in the other problems, they told us that, or we could figure it out. Here, right now, we don't really know what's happening. Okay. We don't necessarily, just knowing 2 numbers here, know what this multiplier is. We can't just divide these or something to figure it out. We're going to have to figure it out using the equation here. So B, we don't know. Okay, X, the time. The time we do know, or we can figure out here, from 1 to 4 p.m., 4 minus 1, that's 3 hours. So our B value on this one is 3. Okay, it's doing whatever it did for 3 consecutive hours. And then Y, that's our ending value. We also know our ending value. They told us what it was after those 3 hours. It was 10. So 10 is our ending value. That's going to go in for y. So in this problem, we're actually going to have to solve for b. We got to figure out what b is. So we want to get that b by itself. So to get rid of this 1250, since it's being multiplied, we want to divide both sides to start with by 1250. That cancels this out. So on the right side now, we got b to the third power. If we go on our calculator and divide 10 by 1,250, we get 0.008. Okay, now we have to get b alone still. They got that power 3. We know from previous units to undo power 3, we want to do not square root, cubed root of 0.008. So on your calculator, do the cubed root and type in 0.008, and it looks like the cubed root of that is 0.2. So that means on this problem, our b value, our multiplier, is 0.2. Now we're not done. They wanted us to write out the exponential function or exponential equation here. So our exponential equation, using that same information we had back here, we can find it out. It would be y equals, our starting value hasn't changed, it's still 1250. Our b we know now, it's 0.2 to the x power. Y and x should always be in your equation if they ask you to write an exponential function. Now we could use that function to figure out how many there's going to be after any amount of time. Let's do another one of those. In number 6, says in 2000 the population of Phoenix was 1,321,045 people, and it increased to this value in 2004. Write an exponential function that shows this. So again, we want to fill in y equals ab to the x. See what we get. Starting value, there's a. We know an ending value, that's y. We can figure out the time here from 2000 to 2004. That's a time of 4 years. So 4 is going in there. The only thing we don't know is b. We're going to have to solve for b. So if we put all this in here, now we're going to figure out what that b value is going to be. Okay, now we're working with some bigger numbers, but that should be fine. We should still be able to figure it out. So first step here, we want to get b by itself. Don't minus this number. It's being multiplied. You need to divide by it. I know it's tempting because we a lot of times we minus, but you need to divide when it's being multiplied. Opposite of multiplying is dividing. So if we divide, that cancels out. And on the right side now, or sorry, left side, we should get a value. So plug that in your calculator and see what you get. So if we type that in, we got 133,1291 divided by, and then plug that other number in. And we get a value of 1.0077 and so on. Now leave that number in your calculator. We want to try to always leave as many values as possible so that our value is going to come out here. So we can write down, for now we can write down some of these, but keep that number in your calculator because we're not done here. We still got to undo power 4. So undo power 4, here we want to be able to take the 4th root. So to undo power 4, we're going to want to take the 4th root of that number. Okay, and the more digits you keep, the closer it's going to be. So on our calculator, I'm going to hit a 4 first. Okay, then wherever you have your x square root on your calculator, that's what you're going to do next. So it takes the 4th root and then type that number, 1.007. Now try to be as close as possible. The more numbers you type in here, the closer your value is going to be to what we want. I'm going to put them all in there. So it looks like our b value on this one is 1.0019. So pretty close to 1.002. So there's our b value. Now we can write our function out. It's y equals our starting value was this one. Our b value is 1.002 to the x power. So there's our equation. Now we can answer anything like on part B, they asked us what's the population in 2015. Well, 2015 minus our starting year here of 2000 means that their time is 15 years. So now we want to take 15, put it in for x, and see what we get. So what is this going to come out to be? Now it's just a calculator problem. You got to plug that in your calculator and see what you get. And if you plug it in correctly, you should come out that the population is going to be 1,361,230, approximately 236. That would be the population. All right. Two other problems here. This is kind of leading into stuff we're going to be doing in the next couple notes. They want us to solve these exponential equations here. So they want to know 3 to the power of 2n plus 1 equals 3 to the fourth. What is n? Well, here's how you can solve these problems. We're going to look at some other ways later. But if these two base numbers are the same and we want to make these equal, well, the only way for these to be equal is if this exponent would equal this exponent. Because the base number is the same, exponents should be the same then. So all you have to do now is set the exponents equal to each other and solve. So we're setting one exponent equal to the other exponent. If we solve this, minus 1, divide by 2, and we get 3/2 or 1.5 as our answer. Okay, so on B, we want to do the same thing, but if you look, we can't just put 2n minus 1 equal to like 1 here. No, though this is an exponent, there's no exponent right now on the other side. So we need to get that to be an exponent. Well, one thing here, this is a fraction. We don't want it to be a fraction. We want it to be a number to a power. So if we look on our left side, our base is 4. We want our base to also be 4 on the other side. So we got to figure out 4 to what power equals 64 here. Well, let's try some things. If we do 4 squared, that's 16. Nope, that's not what we want. If we do 4 to the third power, let's try that on our calculator. 4 to the third, we get 64. There we go. 4 to the third power equals 64. So another way we can write this problem now is 4 to the 2n minus 1 equals 1 over 64 is the same as 4 to the third power. Now, again, we can't yet put these equal to each other. I know our exponent's 3 now, but that's in the denominator. We need this in the numerator. We can't have it 1 over. So what does this turn into if we move it up to the top? Well, we know that anytime you move a exponential to the other side of the fraction, the exponent changes sign. So that would be the same as 4 to the negative 3. Now that these two base numbers are the same, we can set this exponent equal to this exponent and solve it out. So 2n minus 1 equals negative 3. Now if we solve this, we know what n is. Add 1, we get negative 2. Divide by 2, and it looks like in this problem n is negative 1. Just to show you that that works, let's put that in and see what we get. If we put negative 1 in here, you get 4 to the 2 times negative 1 minus 1. That's the same as 4 to the negative 2 minus 1, 4 to the negative 3. Is 4 to the negative 3 the same as 64? Yeah, we've already shown that, but just to show you on the calculator, if you type in 4 to the negative third power, you get that. If you type in 1 over 64, you get that. Both are the same. Okay, so that's one way you can solve exponential problems when you don't know what the exponent is. We'll look at other ways as we go here. All right, try out some practice.